Hello, I welcome you to yet another new series of video, Maths for Chemist, revisiting Maths for Chemist. This is part 1. First of all, the title Maths for Chemist is borrowed from literally a course title recently included in our BSc Chemistry undergraduate syllabus under new CBCS system. A complete paper in the name Maths for Chemist. Of course, it's needless to say that a chemist or chemistry student did not be a master of maths, of course, but since chemistry or so to say physical chemistry particularly, it may often talks in terms of mathematical language, so we need to know a little bit of mathematics as a language. So that's why we need Maths for Chemist. But my title is Revisiting Maths for Chemist, right? So revisiting in the sense that I'm not going to deliver a typical class lecture for teaching some maths for chemistry students. Rather, of course, I will cover the syllabus, but more interestingly and more importantly, my emphasis would be to have a look, have a walk in different ways on different compartments of mathematics, the different points of attraction of mathematics, at different layer, how it reveals its mystery, its cheap attraction, its interest, curiosity, its beauty, and above all its utility. So in one layer, the surface layer, of course it is the utility, but the other layers are no less important. So I would like to have a walk in those layers too. For example, this today's lecture is again divided into two parts. First, of course, the beauty part, beauty of mathematics, part 1, and then literally you can take a break if you want, and then the part 2, which is actually taken from the syllabus, a series, different types of series that I will discuss in the next part. But I would like to start with a puzzle, a couple of puzzles. First, you see summation 1 minus half plus 1 by 3 minus 1 by 4 plus 1 by 5 plus dot dot dot. Let the sum be S1. Another is S2. 1 plus half plus 1 by 4 plus 1 by 8 dot dot dot. Now, let us assume. So the question is what are the values of S1 and S2. So let us assume that on my left, ln 1 plus x log 1 plus x is equals to a series like this, as I have mentioned here. And then you put just x equals to 1. And then you see ln 1 plus 1, because x is 1, it gives you exactly the series as in S1, right? So the answer is, the left hand side is ln 2. So the answer to this first puzzle, S1 is equal to ln 2. And similarly, let us consider another function 1 by 1 minus x, and it is equal to this kind of series, polynomial series. So, and then put x equals to half to get on your left 1 by 1 minus half, and the right hand side is exactly nothing but the puzzle in my S2. So again the answer is S2 equals to 2. And for your information, these two answers are actually the right answers. So is it a motivated step? Let us see. It looks like that to start with, I have taken for each case on my left some function that gives you the actual value of the answer, ln 2 in one case and 2 on the other case. So the left hand side functions I have deliberately chosen as if. On the other hand, the right hand side polynomial expansion, that 2 I have chosen in such a way that they produce actually the S1 summation and the S2 summation, right? So the whole thing it looks like it's a deliberate, motivated attempts in both left side and right side, just to have the right answer to a question, right? Now the question is ln 1 plus x in the first case, is equal to this expansion, or the second one 1 by 1 minus x, is it equal to this? I say that it is, but really how do we get? So that is the question. So yes, the first one, it is a polynomial, of course. The right hand side is a polynomial expansion, and it is of course an infinite series because it goes on and on and on. Now two relevant questions I can raise. Can we express any arbitrary function here 1 by 1 minus x, any arbitrary function as a simple polynomial like this? Can we? This is the first question. And second question, this is an infinite series, so does it necessarily have a finite answer? So infinite series, can it have a finite answer? It's a matter of convergence that we will see. So these two questions we will address later on during my discussion. For the time being, let us get a simple proof that yes, S of this kind of expansion, infinite expansion, is really 1 by 1 minus x. So what is that proof? So let us start with the expansion A is equal to 1 plus x square plus dot 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 up to say nth term. I am taking a finite number of terms, and then multiply both sides by x. So the left hand side is s into x, and the right hand side 1 into x, so x into x, so x square, x cube into x, and so on, and finally xn into x is x to the power n plus 1. So you see the color difference, this 1 and this x to the power n plus 1 are in different colors, and the rest of the terms are in same color, red. It is simply because if I subtract the second equation from the first one, then as you see that x square cube they cancel out, right? So I am subtracting and getting s into 1 minus x on the left, and all the right hand side left red terms are cancelling out, so I get only the blue 1 minus x to the power n plus 1, right? So s is 1 minus x to the power n plus 1 by 1 minus x. Clear? Now since x is, you see, x mod x is less than 1, so fraction, x to the power n plus 1 goes on decreasing as n increases, right? So if n is very large and x of course less than 1, then this term in the limiting condition x to the power n plus 1 would be vanishingly small, or we can say 0. So this part is 0, so the answer is s is 1 by 1 minus x. So s is 1 by 1 minus x. So that is the answer, assumed to be answer in the first person, right? So it looks very simple. To start with, you can check this result by calculator, hand calculator, or by writing a Fortran or in any language program. So you just take a value of x, say 0.5, and then you go on adding 1 plus x square and dot dot dot, say 10 terms or 15 terms, and on the other hand you just calculate 1 by 1 minus x, and you should get the right answer. So it is easily verifiable, right? Now it looks so simple as I demand, but is it really so? At one time it was not so easy, right? And that's why we have got a very important, significant, historically famous Geno's paradox. So before I go into what Geno's paradox is, let us have a few words from Bertrand Russell. Afforded grounds for almost all the theories of space, time and infinity which have been constructed from his day to our own. So that is how significant this paradox is. Now what the paradox is? Well, it's a race between a hare and a tortoise. They decided to go for a race. Now as you see that since I am twice as fast as you do, I will give a half-mile head start. So the hare is being compassionate. He is saying that okay, I run faster, so I am giving you half-mile ahead. So thanks, tortoise says, and then the half-mile. So the hare and the tortoise, and the distance is half-mile, right? So now ready, steady, go. Now they start the race. Now the time the hare travels this half mile, since the speed of tortoise is half of that of here, so by that time it would go 1/4, right? So half mile by here and 1/4 mile by the tortoise by the same time. Now what happens when he reaches at this point? Again, by the time the rabbit reaches the turtle's new position, the turtle has had time to move ahead. So by that time he goes, the hare goes 1/4, and by that time half of 1/4, that is 1/8, is traveled by the tortoise. And the same argument for the next part. No matter how quickly the hare covers the distance between himself and the turtle uses that time to move ahead. So it goes on and on. And here the problem, that can the hare ever catch the turtle? Can it? That is the paradox. How can I ever catch the turtle? As it takes me 1 second to reach his current position, in that 1 second he will have moved ahead again. So I would never be able to catch the tortoise. And it is a total distance covered by, so half mile ahead to start with, and then 1/4, and it goes 1/8, and so on. But it will never be ending, right? So an infinite series. And it is a paradox because common sense tells us that eventually the much swifter hare must overtake the plodding tortoise. Say, for example, if the tortoise is 1 mile ahead of the hare, so the hare was here and the tortoise to start with here, and this is the target. So the distance between this point and that point is 2 miles, and this point and that point is 1 mile. So the time taken by the hare to move 2 miles, because it's twice as fast as the tortoise, then by that time the tortoise should move this distance, that is 1 mile. So that means if they start from here 1 and tortoise from here from the same time, then just they will cover the same 2 miles and 1 mile. That means the distance here to there in exactly the same time. So that time would be taken or required for the hare to catch the tortoise, right? So it's not really a problem, but the way Geno placed it, it was a paradox. But you can't find any logical fallacy, logical problem in that argument of Geno, right? So at the kernel of this paradox, actually we are trying to having something finite in an infinite frame. That was the real problem. And at that time, Geno's time, the infinity series was not that well discussed, right? It was not that well known to them. That was the problem. So resolving the paradox, if the rabbit runs twice as fast as the turtle, then that rabbit runs 2 miles at the same time that turtle runs 1 mile, right? So the paradox is resolved, and the total distance covered is, now since the first mile is 1, then half of these, then half of the remaining 1/4 and 1/8 and so on, but the total is 2 miles that we know to start with. So definitely the answer is 2. The way you are dividing the parts as the infinite series, but the answer is a finite 2, right? So it's not really a problem now after getting a lot of information and knowledge about infinity or infinite series. Well, very quickly let us go for 2 very beautiful demonstrations of this proof, this series. One is graphical, another is chemical. So the first one, graphical. Let us start with a square of 2 square unit, okay, in whatever standard unit, 2 square unit. So half of this, the red part is 1 unit and half is another 1 unit, right? So 1 plus 1, the total area is 2. Now the right hand side part, let me divide it again into 2 parts. So naturally it was 1, so half and half, divided half and half. Now the remaining white square is again divided into 2, and so 1/4 and 1/4. So if you go on by dividing again, so it would be 1/8 and 1/8, and then 1/16 and 1/16. But you notice that the white portion is gradually reducing in its size, right, in its area. So if you again divide, so 1/32 and 1/32, and the white square is even smaller in size, and so gradually you can anticipate very easily that if you go on like that up to many times, then the white portion would actually eventually come to be a point at this point, right, at the corner. That means you cover the whole area, and that the answer you know to start with, it is 2 square unit. So if you go in that way, so the sum of 1 plus half plus 1/4 plus 1/8 plus 1/16 plus 1/32 and 1/64 by 30/64 and so on infinite times, and the answer is actually 2. So it's a beautiful graphical representation, if not proof, but it's a good demonstration. And another is chemical. So we are chemistry student. It's a nice example. Let us consider a zeroth order reaction, and you know the integrated rate equation looks like this: AT is A0 minus KT. A0 is the initial concentration, K is the rate constant, and T is the time, and AT is the concentration of the reactant at time T. And if you just put AT is A0 by 2 at time T half, then T half can be given as A0 by 2K, right? So AT is A0 by 2, so A0 by 2 minus A0 is minus KT, and that gives you KT half is A0 by 2K, right? Now if you again put AT to be 0 in this equation, that means the time taken for reaction to complete, because AT is 0, no more concentration of reactant A is there, that means it is exhausted, so the reaction is complete. So that time if it is T com, that means left hand side is 0, so A0 is equal to K into T com, so T comp is A0 by K, fine. Now so if you think in Geno's footstep, that initially started with A0, then after T half of the first step A0 by 2, and in the second step A0 by 4, A0 by 8, and eventually it will go to 0 because completion is possible in the zeroth order reaction, we know that. And one thing you notice please, that the half-life in the first step is not exactly equal to the second step, to that of the third step, and so on, because half-life depends on initial concentration of that step. So here it should be A0 by 2K, but here the initial is A0 by 2, so it is A0 by 2 by 2K, that is A0 by 4K, and here A0 by 4 by 2K, that means A0 by 8K, and so on. So if we just add the total time T half, T half, T half up to infinite time, then you should get nothing but the total time of completion, that is T comp. So T comp should be equal to sum of T1, T2, T3 and so on. But where T1 and T2 and T3, as I have mentioned, it is A0 by 2K, A0 by 4K, A0 by 8K and so on. So you just take A0 by K out of bracket. So it is 1 by 2 plus 1 by 4 plus 1 by 8 plus dot dot dot. Now on both sides it is A0 by K, you cancel out. So you get 1 on your left, and the right is half plus 1 by 4 plus 1 by 8 plus dot dot dot, right? Now you just add 1 to both sides, so you get on your left 2, and on your right 1 plus half plus 1 by 4 plus 1 by 8 dot dot dot. So that is exactly the series that I am discussing, right? So you get an infinite series have a finite answer from simple chemical kinetics zeroth order reaction. Well, so far the summary goes like that we have started with two series, ln 1 plus x is a polynomial expansion like this, and 1 by 1 minus x is a polynomial expansion like that. Now the question, how can we get these two expansion? We have demonstrated that okay, this is equal to that, but we have not proved the forward way, right? We have not proved. So is there any way how you can show that actually any function you start with can be expressed in terms of a polynomial function, and what would be that polynomial function expansion? Well, before I go into that detailed mathematical steps, let us have a fun quiz time. The question is, what is common among the images? So very quickly I will show you a few images. Of course, while running your video, you can make it pause and have a look for a few seconds, and then you can decide your answer. But now I am going quickly to show you some images, and to tell, you have to tell that what is common among all those images. So the first one, it's a natural scene. This is also a natural scene. This too is one natural one. Well, this is a famous Michelangelo picture drawing. Here again another one, natural scene. Okay, Audrey Hepburn, and this is of course Maharaj Dada, Sourav Ganguly's up drive. Now you have to tell what is the common thing, right? So my experience with many of my friends, really at this time they have given so many answers, but interestingly one or two have given the right answer. Actually it's not that there is a unique answer, but to me, for my convenience in my discussion, it has a unique answer, and that is they are beautiful, the most beautiful. So Dada's updrive, the most beautiful, next to God, as Rahul Dravid told. Audrey Hepburn, one of the all-time most beautiful lady, and all the natural sins, very beautiful, right? So in reference to mathematics, how I'm introducing all this concept of beauty. Well, all mathematics is beautiful, but some mathematics is more beautiful than the other, right? So in that spirit, if I ask a question, is there any most beautiful formula? Well, I suppose that all formula are beautiful, but is there any most beautiful formula? I think it's not an awkward or ridiculous question. In fact, it is a question. And Feynman, at his age 15 of his age, he wrote in his notebook in bold scrawl that the most remarkable formula in mathematics. He refers to actually this most beautiful formula. Now we'll see in the next 2 or 3 slides what is the most beautiful formula, how and why is it most beautiful, and how and why something is at all beautiful. So what is the most beautiful formula? So as you know that actually e to the power I pi plus 1 equals to 0, this is referred as the most beautiful formula, right? E to the power I pi plus 1. It's a discovery of connection between the exponential and the trigonometric functions by none other than Euler, great mathematician Euler, and he used to play. He was used to be called experimental mathematician because he used to play with formulas like a child plays with toys. So that's why he is an experimental mathematician, you will know. So why is it beautiful? First of all, why something at all is beautiful? So the attribute, common attributes to beauty, something like it has to be simple, it has to be profound, and something sensational, and it should be something that takes far away your imagination, and finally it has to be very useful and quite significant, right? So with all this in mind, moreover, the beautiful equation is beautiful because you just see point wise three most important mathematical operations in the same equation: addition, multiplication, and exponentiation, right? It connects the 5 most important constants in mathematics, and they are e, pi, I, 0, and 1. You must agree that these are the a few most important numbers, constants in mathematics. And not only that, it includes 4 major branches of classical mathematics: arithmetic through 0 and 1, algebra by I, geometry by pi, and analysis by E. So it covers so many things in a single equation, right? So far we have discussed the beauty. We have started with the declaration that we'll be singing in our today's concert, raga, and the name of the raga is Taylor and Maclaurin, right? So name of the raga, Taylor and Maclaurin. Then we started with alap, 2 puzzles, and then jod. We have given to demonstration of graphical and chemical demonstration of this expansion. So ragas alap and jod, and then jhala, it's compared to Geno's paradox, and then we have gone for a Mudhala Bandis, that means introducing the most beautiful equation, right? So this is so far we have done, and now as I mentioned that you have a tea break, so it's time for tea, and after coming back, okay, you can give a pause, literally you can give a pause and really have a cup of tea or coffee and come back after a few minutes having refreshed, and then we will see. Okay, well, welcome back. The concert starts again, and we'll see another Dhrut Bandis in Tintal. That means the finding the series, right? That the question I raised, how to find the series, that we will see how to find the series. And bandis in ektal, another Druth bandis, and that would be the examples of e to the power x, sin x and cos x, how these three functions can be expanded in infinite series, infinite polynomial series. And then Loikari. Okay, in any musical concert you have seen that Loikari is one of the most interesting part, and that is finding the most beautiful equation itself, right, from the series expansion. And then finally Sawal Jawab. Well, that is another interesting, when tabaliya and instrumentalist they go for Sawal and Jawab, and that is the application in maths of this infinite series, particularly Taylor and Maclaurin series. And the concept would end with applications of all this mathematics in our physical chemistry, because after all we are physical chemistry students, right? So let us start. Well, a few words from Leibniz. To see the sources of invention is more interesting than the inventions themselves. So basically for our syllabus part, we may be focused with this invention and invention only. That means the final outcome of a discovery or invention. But Leibniz says that it is more interesting and also important to find the sources of the invention. That means the root to that invention, the thought process, the effort of those great people behind those inventions, to have a historical look, maybe to have a philosophical look of all those things. That is no less important for curious students. Well, why I am saying all these things, because now my objective is to go to the root to the most beautiful formula. But before that, we will be discussing the syllabus part, that is Maclaurin series and Taylor series, and we will see how a genius is playing with series. So the question I raised, that can we expand an arbitrary function fx around say x equal to some value a as an infinite series? That means mathematically speaking, it looks like that any arbitrary function fx, can it be expanded like this, where it is the polynomial in x minus a square, then cube, and dot 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 that n. Of course, some coefficients, expansion coefficients are there, c0, c1, c2, and dot 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 cn. Well, the fx can be any arbitrary function, but as per my presumption, the right hand side is of same kind of polynomial expansion. So how is it possible that you will be using the same polynomial but for any arbitrary function, right? It's a question, but the answer is obvious, because no, it's not really the same polynomial. Of course it looks very similar, but the coefficients c0, c1, c2 all are different for different expansions. So that main question is how to get all those expansion coefficients, ci's. If you get all those ci's, then you get the right hand side expansion for any arbitrary function, right? So that is our job. So let me start again from the expansion, and the left hand side for a given problem is known to me, so I have to find only the ci. So how I can find the ci one by one? So one simple trick, that if you use x equals to a, then you see except this c0 term all will vanish. So it's a simple vanishing trick, that you just put x equal to a. That means fx is at x equal to a, that means it is fa. So fa, and on your right only c0 survives, so c0 is fa. So our first part of the job is done. I have found c0, but long way to go. We have to get c1, c2, and so on. So next question, may I use the same vanishing trick? How I can do? C0 is already obtained, but of course the trick, you have to find a little bit more in your trick, and that is how you can make all the terms vanish except this c1 term, and that is very simple. If you take the derivative of this function, then c0 is out, so c1 is there, and here comes 2c2 into x minus a, 3c3 into x minus a square, and so on, and the last term is ncn x minus a whole to the power n minus 1. So now you use the same trick, that if you put x equals to a, interestingly all rest of the terms they vanish except c1, and on your left it is f prime x equal to a, that means f prime a. So C1 is nothing but, on your right only C1 survives, so C1 is nothing but F prime A. So you have got C0 is Fa, C1 is F prime A. So you may be tempted to anticipate the next term C2, trying to follow the pattern. You may say that okay, if C0 is Fa, C1 is F prime A, then C2 is going to be F double prime A, and so on, right? So let us see. Again, I will follow the same trick, that I will take the the next derivative, and C1 will be 0, and the 2C2 would be there, and 3C2 and 2 is coming from here, so 3 into 2 is C3 into x minus A, and finally n into n minus 1 Cn x minus A to the power n minus 2. Now again the same trick, for x equal to A, all the terms vanish, the red letters x minus A vanish except 2C2. So, and on your left it is F double prime A. So F double prime A is 2C2. So C2 is F double prime by 2. So you anticipated F double prime, it's not really so, but very close. It is F double prime A by 2. So maybe now you can be excited that okay, enough is enough, I've got the final pattern, generalized pattern. That is okay, C0 is Fa, then F prime A, then F double prime A by 2. So it was initially F double prime A by 1, now 2. So C3 is going to be F triple prime A by 3. So that the anticipation may go along that line, but let us check. So again I will do the same thing, I will take the derivative, next derivative. So F triple prime A, so 2C2 part is vanishing. Now here comes 3 to C3, 3 to C3, and the next of the terms will contain x minus A. So again put x equals to A, all the terms will vanish except this 3 to C3 term, and on your left it is F triple prime A. So C3 is not really 1 by 3 F triple prime A, but 1 by 3 into 2 F triple prime A, and a 3 into 2 is nothing but factorial 3, right? So I get C3 is F triple prime A by factorial 3. So if you go back, and you can probably accept that this is the general expression you have got, because now 2 is factorial 2, no problem. Here 1, so it's factorial 1. So you are getting the same pattern, factorial 1 by factorial 2 by factorial 3, and the first line it is by factorial 0 is again 1. So now probably it does match with all the 4 terms, and the generalized term may be like this, that Cn is 1 by factorial n f n A. So now you can say yes, I have got the full expansion because I have got the Cn for n equal to 1, 2, 3 dot dot dot, right? So this is how we have found the expansion for an arbitrary function fx. Fine. So I have written again the C0, the C1, the C2 and C3, and in general the formula is like this. Now what I've got, actually I've got, what we got is nothing but Taylor's series. So Taylor series is nothing but a function expansion of fx is C0 plus C1 plus C2 x minus a square and so on. That means I am expanding a function, arbitrary function fx around a, any value a, and getting a polynomial on right with the expansion coefficient, which is having a general formula which involves the nth derivative of a function at x equals to a. So the function is known, so you should be able to evaluate the derivative, any nth order derivative of the function, and then evaluate that derivative function at x equals to a, so you get C1. So you just put C0, C1, C2 and you get the whole right hand side expansion. A simple polynomial expansion for any complicated arbitrary function. So that is the beauty of Taylor expansion. Fine. Now Maclaurin is nothing so new. You just put a equals to 0. So I was expanding the function around x equals to a, right? So a can be any value. So let this a to be equals to 0. Then exactly you get actually the Maclaurin series. So it looks like fx. So C0 you see C0 is 1 by factorial 0, that means 1, and f a is 0, so that means f0. So it is simply a0. And now The next term is x minus 0, a is 0, so x, and c1 is you will get from here, that is the first derivative at 0, so f prime 0 into x, and similarly you get c2 from here and x square here, so it should be x square by factorial 2 f double prime 0 and so on, x cube by factorial 3 f triple prime 0 and so on. So this looks even simpler, but it is only restricted around a particular value a equals to 0. But Taylor series is around any x equal to any a value, right? So let us get a quick example that how we can use this expansion, Taylor or Maclaurin expansion. So one of the interesting number e, a transcendental number, and e has a particular value. So what is the value? How we can get this e value? So let us see. Example, first example, e to the power x. So our arbitrary function is e to the power x, right? So we would like to have an expansion around x equals to 0, that is we are going to use the Maclaurin expansion like this that we have mentioned already. Now f0, that means e to the power 0, so 1. Now f prime 0, f double prime 0, f triple prime 0, for this particular function the derivative of e to the power x, any order derivative fn x, is e to the power x. At x equals to 0, it is e to the power 0, so 1. So that means all are 1, all the derivative terms are 1 here. So the final expansion would be simply 1 plus x by factorial 2 plus x cube by factorial 3 and so on. So that is the expansion of e to the power x. So we have got a polynomial expansion for e to the power x, and it looks like this, right? Some factorial terms are there. And if you put x to be 1, then it is simply e to the power 1, that means e. So that was my question, that what is the value of e. So it is simply 1 plus 1 plus 1 by 2 factorial, 1 by 3 factorial and so on. And if you go on adding a few terms, then you can easily check by a calculator or computer. Its value comes like this. You can check. So that is how actually we get the value of e. And as you know that in your Fortran programming, there is a library function e to the power x, and that exactly uses this expansion, Maclaurin expansion, right? Well, now I will not do the rest of the examples, but I will just mention that what are the most important examples as far as the syllabus is concerned. You just do the same, you follow the same procedure. That means you derive the derivatives of sin x, first derivative, second derivative and so on. That means we will get the derivative, and then you just put in the Maclaurin's expansion and we will get the expansion of sin x, and it would be like this. So similarly you can go for cos x, ln 1 plus x, that is the one of the puzzles we have started with, and then okay, x plus 1 sin x, and then ln x. Okay, so you can do this few examples. One more interesting example is binomial expansion from Taylor series. It's not Maclaurin, it's Taylor, because we'll be expanding around not 0. So fx, suppose the function is 1 plus x to the power n. So if you follow the Taylor series expansion, then actually you will get an expansion like this. Okay, an expansion like this, 1 plus nx plus n into n minus 1, x square by 2 and so on. You can check it, you will get it. Now for n equal to 2, that is our binomial expansion. So we know that 1 plus nx, that is 2x. So n into n minus 1, 2 into 2 minus 1, that is by 2 is there. So it is simply 1. So it is x square. So it is our very popular common formula, a plus b whole square is a square plus 2ab plus b square. So we are exactly getting the same result, but this time through a different route, that is using Taylor series. So that is you can use for n equal to 3 the same formula you can use for n equal to 3, and you will get the formula for cubic expansion function, right? Now we are going to our bandis, Mudhalaya bandis. E to the power x, that we have already derived this expansion, right? Now we will be witnessing that how a genius is playing with series. He took a few bold steps, Euler. First of all, he replaced x, this x, by some imaginary number, say z is I, y. Okay, so x is z, that means iy, simply iy. So what it leads to the result that e to the power x, that's iy, is 1 plus x is iy plus x square, that means iy whole square by factorial 2, iy whole cube by factorial 3, iy whole cube all to the power 4 by factorial 4, and so on. Right. Now replacing x by iy is like playing with meaningless symbols, but Euler had enough faith in his formula to make it meaningful. Why is a question of faith? Because at that time what he did boldly, at that time it was not quite sure that whether it is mathematically an allowed step or not. So he had some intuition, faith, belief that okay, probably it's going to work, and he did it. So only genius can do that. So what we get? So 1 plus iy, I square is minus, so it is minus y square by factorial 2, and there is I cube is I square into I, that is minus I, again minus I, y cube by factorial 3, and so on, y to the power 4 by factorial 4, because it is I to the power 4, that means minus 1 into minus 1, I square, that minus 1 into minus 1 gives you plus 1, so it becomes I to the power 4 by factorial 4, and so on. So if you get the whole expansion after a number of terms, then you will see that plus and minus both signs are there, some are plus signs, some are minus signs, and also notice that some terms include I and some other terms they don't have I in their part. Okay, so this is something like this. I have separated in two classes, one in red color, that is without the I, the terms in red are not having I, and in black they are all having I, either plus or minus, but they are having I. So classified into two groups. And here comes another bold step from Euler, changing the order of terms, which is not necessarily valid for an infinite series. So at that time he was not quite sure that what he is going to do, it's not an allowed step, because infinite series was not that known to them at that time. So what did he do? He took the red ones in a single bracket. That means he has changed the order. He picked up the red ones in one bracket, and he picked up the the black ones in another bracket. Of course, the black terms include I, so I is taken common, and so rest of the terms looks like this, and all this red without I. Now, if you remember a few minutes back, I have shown the expansion of sin y and cos y. I didn't do, but I quickly did show you. And then, if you just go back a few slides, or you can have a pause and just drag back your cursor to get that slide, you will see that sin y is like this and cos y is like this, red. So I have again used two different colors deliberately, because this red part in this expansion is nothing but this red part. That means this part is actually cos y, and exactly the black part is nothing but this part other than I, so this is sin y. So what you get, very interestingly, that e to the power I is now getting trigonometric, right? The first part is cos y, this red part, and the black part becomes I sin y. So e to the power iy is cos y plus I sin y. And now we are very close to our beauty. If you choose your y to be pi, you have every right to choose. So e to the power I pi is cos pi plus I sin pi, and cos pi is minus 1 and sin pi is 0. So it gives you e to the power I pi is minus 1. So e to the power I pi is minus 1, right? So we have proved the most beautiful equation, e to the power I pi equals to minus 1. So EI pi relation, the most beautiful equation, and here quickly a couple of interesting problems from EI pi. I will show it very quickly because you can get it from the slide later on. The first one is I to the power I, imaginary to the power imaginary, right? So is it too far from reality? Okay, behold, before you make any comment, I to the power I is actually real, so it's not too far from reality, though the left hand side is imaginary to the power imaginary. So when you are too much imaginary, actually you are very much realistic. Well, e to the power I theta, so let me just use that same expansion, cos theta plus I sin theta. For theta equal to pi by 2, you will get e to the power I pi by 2 is cos pi by 2 plus I sin pi by 2, and that means 0 plus I, that is simply I. So e to the power I pi by 2 is actually I. So that I will be using e to the power I pi by 2. So I to the power I, the I is e to the power I pi by 2 as we have seen it, and to the power I is okay. Now I is I square, that is minus 1, so it is e to the power minus pi by 2, that means 1 by e to the power pi by 2, and that has a definite positive value. So I think it's very interesting that I to the power I is actually root of 0.2078 dot dot dot. And another one, this is, you can take it as an exercise, that it is one of the important expansion in relation to the research of pi, right? This is probably the first expansion of pi, but that was used that was on the basis of this expansion. So you can go through later on. And now we'll be going for use of Taylor's and Maclaurin series in mathematical aspects, right? The first one is Newton method for finding the solution. So in not only purely mathematical but also in numerical analysis, computational aspect. And not only that, when you will be using this numerical analysis part in your physical chemistry problem or any physics problem, for finding the root using Newton-Raphson method, actually will be using this expansion, and this is nothing but iterative step that you are modifying some new x value from this old value by this formula, and this formula is based on actually Taylor series, right? So here a couple of integration, that sine x squared dx, it's not easy to integrate otherwise, but if you just use the expansion of sine of something, as I have shown the sine expansion, then you can do the integration part by part, and that is simply polynomial expansion. So the part by part integration is now very trivial, and you can get the answer to be this. So that is also another use. And similarly, the same kind of in kinetic theory of gases, we have encountered this kind of integration, e to the minus u square du 0 to some value, and that you use this as standard integral, right? Standard integral used in our numerical problems. But where from we get this standard integral, right? If you ask the question, the answer is of course from Taylor series, and the answer comes out to be this. You can check easily by this expansion which I have got from Taylor series. You can verify this result by program after understanding what do loop and array etc. in programming language. The fourth one is sin x by x dx. This is also a typical complicated integration, but again by using the expansion of the functions you can get the value, exact value of this integration. Finding limits using Taylor and Maclaurin series. Finding limits. So not very general and common limit, but very specific and complicated limit, where limit fx by gx, this kind of problem where x tends to a, but particularly when these are of the form something by undefined 0 by 0 case or 0 by infinity case. This is the typical peculiar cases. For example, sin x by x, x tends to 0. So you know that it gives you sin 0 is 0 and x is 0, so 0 by 0 case, and which is not very easy to find this limit unless you go for some special trick. So one of the trick is of course using Taylor series or Maclaurin series expansion. We just use the expansion of sin x as I have shown earlier. This expansion you are using for sin x and dividing by x, then you cancel out, and finally you can now in a position to put your limit without any 0 by 0 type of problem, and you get the answer to be 1. So that is an important use of this series to bypass the very typical problem of finding limits. Another example is given 1 minus e to the power x by x. The same problem, it's a case of 0 by 0 case when x tends to 0. But again, if you just use the expansion of e to the power x, you please do it. It's a very simple exercise. And then again, we can show that the answer is minus 1. Well, at this point, you can say that, sir, why should we go for this complicated expansion, etc.? Because there is a very beautiful L'Hopital's theory, which can help me to find this kind of complicated 0 by 0 case limit. Well, so that we know, and the prescription from L'Hopital is that if the case is 0 by 0 or 0 in infinity or infinity by infinity, and then you just do the first derivative. So if this problem is problematic, this part is problematic, fx by gx, then you take the derivative of fx, that is a prime x, and gx to be g prime x, and you just put the same limit x tends to a. Now, if again this gives you, still it gives you 0 by 0 or 0 by infinity case, then you go on taking the higher order derivative and so on. So that's the prescription from L'Hopital, right? But my question is, the sin x by x and cos x by x, okay, sin x by x, if you take the derivative, because this is a 0 by 0 case in general, so sin x derivative cos x and x derivative is 1. So now you put x equals to 0. So cos 0 is 1 by 1, so the answer is 1. And similarly 1 minus e to the power x by x, the same thing, you will get the correct result to be minus 1. So this is a beautiful simple way of L'Hopital. But the question is, if you again, if you are just handling the invention, that's okay at the outset. But if you want to see the source of this invention, then you will see very surprisingly that again at the heart of this L'Hopital theory is nothing but that same Taylor and Maclaurin expansion. So I am not explaining it, but you can follow it later on, that why the L'Hopital rule is what it is. It is because of the Maclaurin expansion, right? Now finally, we are going to almost conclude the concept after Sawal Jawab, Laikari. Now it's going for Sawal Jawab, right? Field chemistry one side, the Tabaliya and the Maclaurin is the main instrumentalist. So it's a Sawal Jawab between a Tabaliya and the instrumentalists, right? Zakir Hussain and Saeed Parvez. Well, so the first one is osmotic pressure. Well, this portion I will I can go very quickly because you are being chemistry student, you have come across all these things. I'm just compiling at a single frame that how and where we have used this Taylor or Maclaurin expansion. Osmotic series pressure, virial coefficient of Van der Waals gas, temperature dependence of CV for diatomic gas, temperature dependence of CV of solid crystal. Actually it was done by one of the 5 papers of famous papers of Einstein. And another is intermolecular potential VR in spectroscopy. So at least I have compiled 5 examples, you may find even more. And for example, osmotic pressure. Osmotic pressure at one point of your calculation, you get an equation like this. And now ln 1 minus x2. So here we will be using that expansion that we have taken as an example, or it is one of the, in fact, the puzzle I have started with. So I think you can understand that why I have started with a puzzle, and that particularly with this kind of puzzles, right? So this is ln 1 plus x is this expansion. So 1 minus x2, so x is minus x. So you see, if x is very small, then you can neglect the higher terms. So it is ln 1 plus x is simply x. So ln 1 minus x simply minus x2, right? So it is minus x2, right? ln 1 minus x2 is simply minus x2. So the whole thing is minus minus plus, so RT ln x2. So that is as typical class 12 level reduction that we have done in osmotic pressure. But at 12 level, we probably have not were curious enough to ask the question that, sir, you are using this kind of approximation, where from you are getting this approximation? And actually now we are getting the answer to that question, that approximation is coming from this Maclaurin or Taylor series expansion. And similarly, the other examples, these are the typical deduction that we teach in our thermodynamics or kinetic theory classes. Virial coefficient for Van der Waals equation, and here we use actually the expansion of Taylor and Maclaurin. So I'm skipping this part. And similarly, another example is temperature dependent of CV, diatomic gas. Here also you use the expansion of e to the power something, right? and finally you get the right answer. Well, another is that the famous paper of Einstein, temperature dependence of CV of solid crystals. Here again we can use some expansion of e to the power x, right? 1 plus x plus x square by factorial 2 and so on, and so order of x square, and we neglect all those terms, and then finally we simplify the equation to get the correct result, high temperature limit of classical limit of CV. And finally the intermolecular potential spectroscopy. We expand the anharmonic oscillator potential to start with to model dimolecule as a simple harmonic oscillator, right? It's simple model, but in reality the molecule is not really simple harmonic, but it is anharmonic oscillator. So what would be the anharmonic oscillator potential form or function? So what we do is the V is the potential function in terms of the internuclear distance r, and around r equilibrium, if we expand that potential function, then you get the Taylor expansion actually, and that's all about the anharmonic oscillator function. So the first derivative, second derivative, polarizability, hyperpolarizability, all these terms, they actually arise from this expansion, right? And that's how we get actually the very famous Morse potential, which is exactly solvable Morse potential, and at the heart of this potential it lies the expansion, right? So finally, at the references, well, two different color are used. The black ones are actually the popular reading of books. Imaginary tale, the story of square root of -1, pi a story, E a story. So it's a trio of three very interesting and very favorite books of mine, stories of I, pi and E, and then of course two interesting numbers 0 and infinity, and okay, Evan Stewart is a very famous writer, you know. And the red colored are for my chemistry part, the mathematics of physics and chemistry, Morgan and Murphy. It's a very old and classic book. Mathematical methods for scientists and engineers, Maclaurin. This is the book for me. And mathematical methods in the physical sciences, this is also a very interesting book. And physical chemistry, of course, my favorite book, P.W. Atkins. So here I conclude the part 1 of my new series, Maths for Chemist, and I will come back with the second part probably with another topic from Maths for Chemist. So far so good. Thanks for watching, and please make comments and suggest how to improve this quality and content and everything of this presentation. Thank you very much. Good night.